Come on in. So I will say something about 9 Nielsen theories. Well, first of all, thank you all for coming here and thank you for the invitation. It's really great to be here. This is my first time in Spain and everything is great and I'm glad to be here. And please, if you have questions, please interrupt with questions about the mathematics. If you have questions about America and our president, you can ask me after. So I'm going to talk about 9 different Nielsen theories. I decided to do 9, so each one will be kind of short, and if you ever get bored, just wait a few minutes and I'll be to the next one. So hopefully it will be exciting. These are all the ones, but we'll get to them eventually. So the first one is the Nielsen theory about fixed points, and this is the usual Nielsen theory. If somebody is talking about Nielsen theory, it's probably this. It's about fixed points. They are points where f of x equal x. And you can see them on a picture like this. They are points where the graph of your function intersects with the diagonal. This one here has 2 fixed points. And the big question which we ask in Nielsen theory is how can the fixed point set change when f is changed by a homotopy? So if you just think of this curve here and you move it a little bit, what is the effect on the set of fixed points? All right. Generally, we're going to work with self-maps. It has to be self-maps if you talk about fixed points, but on compact polyhedra is the standard setting for Nielsen theory. It can be slightly more general than that, but this is the usual. And, just for our cases, I'm going to be talking about examples on the circle a lot. Because I want one-dimensional is a simple case, but it has to be compact, so it should be the circle, not the line. So I'm going to draw my maps kind of like this. This is the graph of a function on the circle. So the domain is the interval with the endpoints identified. So when we draw the curve, it has to, and the codomain the same. So when it goes off the bottom, it has to come up the same place, like Pac-Man. All right. And the question, anyway, what can happen to the fixed point set when f is changed by a homotopy? Typically, we're going to focus on the cardinality of the fixed point set. How many fixed points are there? Here, there's 2, but could we make... can this number 2 be increased by homotopy? Can we make more than 2, or can we make less than 2? That's the question. So, actually, only one of those questions is interesting. If you want to increase the fixed points, this is always possible to increase by homotopy, because you can just do something like this. If you already have one fixed point, you can just make lots of little wiggles, and it will create many more fixed points. So increasing the set of fixed points is not very interesting. Nielsen theory generally focuses on minimizing the number of fixed points. That is much more interesting. Like in this particular example, can you change by homotopy to make only one fixed point instead of 2? All right. This is the thing that Nielsen theory was designed to calculate. We write this as MF. It means the minimum number of fixed points among all maps which are homotopic to f. All right, this is the minimum number of fixed points. And the basic idea that is used to approach this comes from Hopf and Lefschetz and Nielsen in the 1920s, around that time. There are 2 basic ingredients to every kind of Nielsen theory that I'm going to talk about. 2 basic ingredients are the fixed point index, and this was basically done by Hopf and Lefschetz, and the fixed point classes, which is due to Nielsen. So I'll talk about each one of those 2 things. The first is the fixed point index. This is an integer valued index, which is kind of like a multiplicity for a fixed point. And in this simple example, in dimension 1, it's very easy to talk about the index. It just is related to the orientations when the graph passes through the diagonal. So if it's going down like this, then that's a +1. If it's going up, then it's a -1. So this is how the index works in dimension 1. All right, and you'll notice this index is well behaved when we do homotopies. If you move the graph a little bit, the index stays the same, right? It just moves a little bit. Now, I could move even further, but watch what happens. This counts as a 0 index if the graph is meeting but not crossing the diagonal. We call that 0, all right? And then it can move entirely off, all right? So this is this sort of basic setup of the fixed point index. And you'll see a fixed point index of 0 means that that point can be removed by homotopy entirely. You can pull the graph all the way off the diagonal, and there's no fixed point anymore. And when two fixed points combined, the index is additive. Remember over here? A +1 and a -1, they come close together, and then they meet, and now it becomes a 0. So this fixed point index has an additivity property when you do homotopies with fixed points. All right. This is similar in higher dimensions. You can't really draw the pictures in higher dimensions, but the fixed point index is defined not what I'm showing you. The pictures are all dimension 1, but you can do similar things, and it's basically like sometimes called the oriented intersection number of how the graph of the function is intersecting with the diagonal in the space. All right. So big question that we have then is, in what cases can two of the fixed points combine? Remember, we are trying to reduce the size of the fixed point set. If you had two fixed points, can you turn it into one? What is necessary in order for that to happen? All right. There is a necessary condition that we can see pretty easily on the graph. It is that this region here in the graph, or in the, I guess it's not in the graph, in the space that the graph lives inside, this region right here has to be contractible, because if you want those 2 points to come together, this region will shrink down it will disappear, right? So that region in between the graph and the diagonal must have no holes in it in this space, because if there is a hole in there, there's no way you can bring the 2 points, the two fixed points together. All right, we can be more precisely about it. If I have two different fixed points, x and x prime, I draw them like this, then there must exist a path, and this is going to be, if I want to combine those 2 points, this will be the path on which I'm going to bring them together. So there has to be a path, first of all, and that path must have the property that if I do the function to this path, since x is a fixed point, it means this first endpoint, if I plug the function in, this path, its first endpoint will still be here, and also this path it will end still here, because those are both fixed points. And the condition is that this region in between these two paths must be no holes in it. In other words, this path, fixing the endpoints, this path is homotopic to this path. That's the condition. So to combine x and x prime, there must be some path with this property. Gamma is homotopic to f composed with gamma as a path with fixed endpoints. All right. In this case, we say x and x prime are in the same fixed point class. And this is the second ingredient of the Nielsen theory that I was talking about. So every point has an index, +1, -1, or 0. And then also the fixed points, some of them will be in the same class as one another, and some of them will not be. All right. Actually, this relation about homotopy of paths here is a little inconvenient to work with sometimes. And it can be phrased purely in terms of the fundamental group. This will look a little more complicated, but it's often easier to work with just because the fundamental group is something that we all understand. So if I'm talking about the fundamental group with base point x0, the base point is somewhere over here. If you want this to work, you must choose the base point also to be a fixed point of the function. But anyway, you can do some things which will look slightly complicated. You choose a path from the base point to x, and then there's also f compose a. Now this path may not be contractible inside, but it's just something. This makes one group element alpha, which may be trivial or maybe not. And then you do the same thing over here. And it turns out the contractibility of this, you can rephrase in terms of, rather than going here and then back here, you can go around here and back here and around here. So this is slightly complicated, but this is the condition that it ends up giving you. So when x and x prime can be combined, there exists a loop z. So in this picture, z would be the one which goes maybe all the way around the outside, something like that. But anyway, this is the algebraic condition that it all boils down to. So you can actually calculate when two functions are in the same class or not, according to this algebra in the fundamental group. And if the fundamental group is a sort of nice group, then this is not so hard to calculate. This relation here is called twisted conjugate. You can see alpha and beta. This formula over here basically says z beta z inverse. That would be conjugacy, but we additionally have this. This is the induced map in the fundamental group, the induced homomorphism. So it's not exactly conjugacy, but it's similar to conjugacy. All right. And then the classes that you get are called the fixed point classes. They're also called the Reidemeister classes. So this is the second main ingredient. And like I said, depending on what the group is that you're talking about, the Rademeister classes might be easy or hard to compute. It's fairly easy if your group is finitely generated abelian group, then you can express the induced homomorphism as a matrix, and all of these calculations are pretty straightforward. All right, but for more general groups, more difficult groups, this is called the twisted conjugacy problem, and it's like a purely algebraic thing that you can talk about. Like for instance, for free groups, this is a hard problem to solve in general, the twisted conjugacy problem. Okay, so anyway, these are our two ingredients, the fixed point index and the fixed point classes. We say a fixed point class is essential when its index sum is non-zero. So this means you have some fixed points, which maybe could be combined, but if you look at all the plus one, minus ones, it adds up to non-zero, all right? And the Nielsen number, this is the definition of the Nielsen number, is the number of essential fixed point classes. So it's the number of classes of fixed points which have index non-zero. All right, and then this is the sort of why anybody cares about the Nielsen number. This is called the Nielsen fixed point theorem. It's a homotopy invariant lower bound for the number of fixed points. So this Nielsen number is a lower bound for the minimum number of fixed points that I said at the very beginning is the main goal of Nielsen theory. And these two numbers are equal when x is a manifold of dimension not 2, so dimension 1 or greater than 2. When x is a surface, they can be not equal, but it's a bit of a strange sort of ironic. In Nielsen's original work, he was thinking only of surfaces, and he created the Nielsen number so that they would be equal on surfaces, but this is actually the only case when they are not equal. Yeah. All right, so this is the basic Nielsen fixed point theory. You make the classes, and then you see which of the classes are index non-zero. And then the classes, you can, within each class, you can combine them into a single fixed point, and so you get only that many fixed points. All right? I'll just say, on the circle, all of this is easy to compute. If I write the pi1 of the circle as, has a single generator, I'll call it A. Then, for example, this example that I wrote a few times ago, this one, the index is a +1 because the line is going down through the diagonal. And if you work out the algebra, you can see this is the class of this one, whereas this one has a different class, a different fixed point class. It's really because this graph, it wraps around the circle before it gets to this point again. And so the fixed point class will be different. But once you see this picture, my question at the very beginning, can you actually combine those two fixed points and make one? The answer is no, because they have two different fixed point classes. And so it's impossible to bring them together. All right, two different fixed point classes, each has index +1. So since they're +1, it means it cannot just disappear all by itself. And so that means the Nielsen number here is 2, which means the minimum number of fixed points is also 2. You can't get fewer than 2. We cannot reduce the number of fixed points anymore. All right. In general, there's a formula, so this is all worked out for a circle. If you have a map on the circle of a certain degree, the Nielsen number is always equal to this. So this example was a degree -1, it's going down, and this would be -1, subtract 1, it's -2. Absolute value is 2, all right? So this is the formula for the Nielsen number on a circle. And then another easy case is a torus. A torus works out nicely. There are generally the Nielsen number is very well behaved with respect to products, and since the torus is a product of circles, it's not so hard to do this. So on a torus, every map is homotopic to a sort of linearization on the torus, and this is the formula for the Nielsen number on the torus. And you can see in dimension 1, these are the same, but this is determinant of A minus the identity matrix. All right. You will see these formulas appear again in the future. These are the basic examples of the Nielsen fixed point theory. All right, this is the ordinary Nielsen theory. That was the first one out of 9. All right, okay, number 2, coincidence points. This was actually the first variation of Nielsen theory. So in the many years since it was created, about 100 years ago, Nielsen fixed point theory came along. There have been many variations of the basic idea. So the idea of the fixed point index and also the idea of the fixed point classes. You can use these or similar things to solve other kinds of problems, not only about fixed points, but about other things. So the first one of these that happened, historically speaking, is coincidence points. And actually, Lefschat's original work Usually we know of Lefschetz, like Lefschetz fixed points theorem. This is what I know Lefschetz about. But actually Lefschetz originally did this in terms of coincidence points. All of these techniques that I just discussed about the fixed point set can also apply to this we call the coincidence set. If you have two different maps, f and g, I'm looking for all the points where f of x equal g of x, all right? For instance, like this. Here I have two different functions. These are two colors. Sorry, they kind of look the same here, but there's a blue one and a red one. And you can look for the places where they intersect. Those are the coincidence points, all right? And I'm sure you can see, well, this is basically like the fixed points, only I'm not talking about intersecting the diagonal. I'm talking about intersecting something else, all right? So just like before, though, we can define a coincidence index of any isolated coincidence point. And again, it's just going to be +1, -1, depending on if it sort of goes down through or up through, all right? And we also have coincidence classes. I'm going to draw the paths, although it's going to look a little different here. Here, if I have x and x prime are both coincidences, I want to take a path between them, and then instead of having that path and also f composed of that path, I have two maps, f and g, right? So first of all, plug these into f and g both. Since these are both coincidence points, this one goes to the same point here, and this other one goes to the same point here. And then the map, you can plug in f, or you can plug in g. So I get one image under f, one image under g, and now the condition is these must be homotopic here. All right, so if that's true, then you can see, then it actually will be possible to bring these 2 points together in using a homotopy. As long as it's not dimension 2, there are problems in dimension 2. But all right, and this relation, I'm not going to draw the more complicated picture, but this relation you can also express purely in terms of the fundamental group. It's called the doubly twisted conjugacy. It looks like this, which looks the same, only here it used to be z, but now it's g of z. So this is the induced map of G in the fundamental group. And again, this is a purely algebraic decision problem, which you can try to talk about, do the algebra. All right, and this is called the Nielsen coincidence number. So this is defined to be the number of coincidence classes, which have non-zero coincidence index sum. And it's the minimum number of coincidences. Interesting to note, this is allowing homotopies in both maps, right? All maps homotopic to F or homotopic to G. All right. Of course, all of this is a generalization of fixed point theory. If you let G be the identity, then everything that I just said is the same as the fixed point theory. So this is why it was a first sort of natural generalization of the fixed point theory. One thing that's actually very different, though, in coincidence theory, if you want to talk about this, f of x equal g of x, it's no longer necessary for f and g to be self-maps. For fixed point theory, it always has to be self-maps. And this actually changes the theory quite a bit. Many new things to consider. For example, I can do this where the domain space and the codomain space are different. And actually here they're very different. They're different dimensions even, all right? And if you think about how this works out, if I go S1 to T2, this dimension 1 up to dimension 2, the graphs, these two things, they have a graph, and they will be one-dimensional graphs, but they live inside this space. We have two one-dimensional graphs inside of a three-manifold, right? S1 cross T2. This is actually T3, I guess. But we have two one-dimensional things inside of a three-manifold. Actually, those two graphs, they can always be separated just because of the dimensions, right? So in sort of a general position, we can always make the coincidence set empty in this case. So actually, this case where the domain dimension is less is not all that interesting, because we can always remove all the coincidences in that case. But what if we do the other way around? Here the domain dimension is larger than the codomain dimension. Now the graphs, by the same thing I just said, now the graphs will each be two-dimensional submanifolds of a three-manifold. And actually now they will, like in a general position, they will intersect along a one-manifold, right? Because this will be sort of four total dimensions inside of a dimension 3. And so actually this coincidence set will in general be always infinite. So now there's many, the theory is very different because you're no longer counting individual points. You're counting something which is in general case going to be infinite. And so I'll just say counting this is very different in this case. This is referred to as positive codimension Nielsen, or positive codimension coincidence theory, which actually is very different from the Nielsen fixed point theory. Anyway, in general, if we have maps of orientable is actually necessary in order to define the index in a consistent way. But if we have some domain dimension and some codomain dimension, if the domain is less, then we can always make the coincidence set empty. This is what I just said. If they're equal, then actually this is very much like fixed point theory. So in that case, we can make the coincidence set into a finite set of points. And then you do things that are very similar to Nielsen fixed point theory. And if the domain dimension is larger, then this is generally you can't make a finite points because it's a submanifold of dimension, I should say, greater or equal to 1, all right? This is the positive codimension case, which is very different. And I personally actually don't know very much about this, all right? So anyway, the most natural Nielsen coincidence theory is for maps between orientable manifolds of the same dimension. In that case, everything looks very much like fixed point theory. Otherwise, it's quite different. And we get some nice formulas. If you remember this formula from before, it used to say degree f minus 1. But now you change the identity to a g, you get this. This is what everybody would expect the formula to be on the circle. And on the torus, maybe you can imagine it's this. This used to have an identity matrix right here, but now instead of identity, I have this G with the linearization B, and this is the formula for coincidence number on torus. Torus of the same dimension, of course. It's a nice formula. Okay, that was the second one. You ready for number 3? I'm going to accelerate the numbers. These ones will be more shorter. An interesting variation is what about more than 2 maps? All right, so this is a coincidence set of, I said, many maps. This doesn't really have a good name in my opinion, but this is more than 2 maps. So like this, here's another example on the circle. I'm going to draw 3 maps. There's one, there's another one, and there's a third one, all right? Where are the points? And what I want is a point where all of these maps agree at the same time. On this picture, there are none, but I'm looking for 3-way intersections. So, and actually, in general, if you're talking about graphs of this nature, you can always change something by homotopy so there's no triple intersections, right? So this coincidence set of all 3 maps is empty. And because, like what I said, for more than 2 maps, this coincidence set will typically be empty. And again, it's because of the dimensions. I had three one-dimensional things inside of a 2-dimensional space, and so you can separate them. But we can get a nice theory of the dimensions are just right. So if you make the domain, the codomain have this dimension and the domain have this dimension, where this k is how many maps there are, then actually you can make the coincidence set finite, and you get a coincidence index and coincidence classes and all of that stuff you can do in this very specific setting of these kinds of dimensions. All right, I'll just say this was done by Dobrenko and Kusharsky in 1990. Although this was like, they wrote a whole paper about sort of something else, and they had like one little footnote. They said, by the way, if you do this in a certain way, you can get this coincidence theory of many maps. I wrote a paper 20 years later with the same idea because I didn't see the little footnote. So after this paper was published, somebody came to me and said, "Hey, did you know that this was in this old paper?" And I didn't know. Sorry. And then somebody else a few years later didn't see my paper either, and also didn't see this one, and they did the same thing again. So I guess maybe it's a good idea then. It's been done 3 times without knowing about the other ones. Anyway, here's the torus formula for that one. If you have several maps here, you get this. These, because of the dimensions here, these matrices are not square matrices. But if you stack them up in exactly this way, you get a square matrix. And this is the determinant formula, which again is a familiar formula from before. All right, that was the coincidence of many maps. You ready for the next one? How about periodic points, okay? The question here is given some natural number n, can we look at the set of periodic points like this? All right, these are the n periodic points. There is a simple approach, which turns out to be a bad idea. The correct approach is much more complicated than it seems at first. The simple approach is you just look at this and you say, oh, this is just the fixed points of f to the n. And so we just do Nielsen theory, but use f to the n instead of f, all right? And I want to do this in a homotopy invariant way. So I wanted to look at something like what's the minimum number of periodic points of period n, which can be achieved by changing f by a homotopy. That's the idea. All right. So we can consider the Nielsen number of f to the n, but this actually is not what we want. It's because this Nielsen number considers all maps homotopic to f to the n, and that is different from all maps homotopic to f, and then you do the nth iteration, right? These, I mean, at least maybe they're different. They're not obviously the same thing, and actually they are not the same thing. This is more restrictive, right? We don't want to change f to the n into some other map. We want to change f into some other map and then look at the iterations of that other map. This is more restrictive. And there is a difference. Here's an example. Here is very simple. This is the map of degree 1. It has one fixed point, and this one fixed point cannot be removed. So all maps homotopic to f have one fixed point, and that means automatically they also have a periodic point of period 2, which comes from that one fixed point. So this set of periodic points of period 2 cannot be made empty by a homotopy of f, because f must have one fixed point, and that will have one periodic point. But this second iteration of f is the identity. If you just think about do this twice, it is the identity map. And the identity map on a circle can be changed by homotopy to remove all fixed points, all right? So we can remove all the fixed points of this map, but we cannot remove all the periodic points of period 2 from the original map f. So there is something kind of interesting happening here rather than just Nielsen number of f squared, all right? Yeah, so the minimum number of fixed points of f squared is 0, but the minimum periodic points is 1, all right? And so there's a Nielsen theory for this too. It's a little complicated. I'm not going to get into all the details. This was done by Zhang in the 80s. For n periodic points, we use the fixed point classes of this map f to the n, but we have to be careful about observing which ones of these come from the lower iterations. And so we also consider the lower iterations when k divides n. And then there's this they call it the algebraic boosting map, which takes a fixed point class in a lower iterate and raises it up to a fixed point class in a higher iterate. It looks like this algebraically, which is a cute little formula. But anyway, the Nielsen periodic number is defined by, you count the essential classes, that is, you use the ordinary fixed point index, the essential classes of f to the n, but you also have to count the essential classes of the lower iterations and consider them all together. And Zhang actually made two different Nielsen periodic theory invariants. There's one for counting the points of period n, and then one for counting the points of least period n, these are different numbers. You know, this one is less than that one. But you have to handle them in two different ways. And I will refer you to Zhang's book if you're interested more about the details of that. All right. All right, number 5. Multi-valued fixed point theory. So this is another variation. Nielsen theory has been attempted for several different types of multi-maps. I'm going to write it this way. It means a multi-valued function from x into x. Fixed point is defined to be a point where x is an element of f of x. F of x is a set, and it's called a fixed point when x is a member of f of x. And the most natural, like kind of the easiest setting in Nielsen theory is what they call the n-valued maps. This means every x gives you a set of n elements in the image. Exactly n, so never fewer than n. All right, this is called the n-valued map. So this right here is an example of a 3-valued map on the circle. If you look, every point in the domain has exactly 3 values above it. And what are the fixed points? There are these 2 points here. These are points, again, where x is an element of f of x. And you can see, again, they are just intersections of the graph with this diagonal line. And so you can imagine, you can probably do all the same stuff in this setting. It's not all that different from the ordinary fixed point setting. So these fixed points still have the same fixed point index you can use here, the +1, -1. The fixed point classes are a little bit weird. I'll show you the paths for that one. So in this setting, you have a path from x to x prime, 2 different fixed points. Now, I'm going to apply the map to the path like we did before. But remember, the map gives you n values. So what this looks like is, first of all, x itself is part of this. I'm doing 5 values for this example. So x is one element in this 5-element set, and x prime is like some other part of this 5-element set. And then where does this path go over here? Well, it goes to 5 different paths over here, because that's what you get when you apply the function to all of these things, all right? And then what's the condition that I want? So the condition for being in the same fixed point class in this setting is gamma. The original gamma is one of these over here, and it just says that one of those paths that you get from this F composed gamma is homotopic to the original gamma, like this. Only one of them has to be. Actually, only one of them could be, but this is the relation that we use.
In this case, the F map is continuous in some way.
Yes, it's continuous. Yeah, the continuity is, so it's n values, which means you can think of such a map as a map of x into the Cartesian product x to the power n, where you remove, it's not allowed to have duplicate values, and then it's like the subspace topology of x to the n, and then it's continuous in that way.
Space.
Yeah, right, yep. Yeah, great. So this is how the fixed point classes are defined in this multi-valued, the n-valued setting. This is much more complicated, though. If it's not exactly n values every time, it becomes a lot harder to do this, to make it work. All right, this is the condition. There exists a path from x to x prime such that F composed gamma includes one path from x to x prime over here, which is homotopic to the original path gamma. All right? And if you try to do the algebra, you can do a twisted conjugacy approach to this. Instead of just pi 1, you get this stranger group. This is a semi-direct product, pi 1 to the n, because there are n different values, but then there are n values coming in a list, but you have to consider permutations of the elements, so this is a little complicated. This Nielsen theory is due to Schirmer in 1984. Helga Schirmer was someone who really liked creating different types of Nielsen theories. And Bob Brown, she wrote 2 papers about this in the 80s, and then nothing else. And then somehow, I don't know why, but Robert Brown, 20 years later, decided this was really interesting. And then since then to now, there's been like 30 papers about n-valued Nielsen theory. So everybody became interested in it again after a while. I don't know why. Anyway, here's the formula for a circle map. I wrote it the other way around. But remember, this used to be 1 and degree. For n-valued, it's n. Very nice, in my opinion. All right? And for a torus, it looks like this. N times the identity matrix. Instead of, it used to be just the identity matrix. So if your map, if your n-valued map F has a linearization, then it has this formula. Although there's actually, we have learned that not all n-valued maps on a torus have this kind of nice linear version, because there are strange things that you can do if you have n values. So this is still not entirely understood. All right. Okay, number 6. I got like 10 minutes left. Number 6 is Nielsen root theory. This is a very simple one. This is actually implicit in Hopf's work, but it was kind of resurrected or clarified by Brown and Schirmer in the 70s, I think, maybe 60s or 70s. Anyway, if you have one map, x to y, and you just choose a point in y, a root, we call a root is just some point in the preimage of C, some point in x which goes to C. And you know, this is another way to say the same thing. F of x equals C, all right? And when you see this, you can say, oh, well, this is kind of like f of x equals g of x, where g of x is a constant. And so you can do a Nielsen theory for that, thinking of this as if it was a coincidence problem. But it's a very simple kind of coincidence problem, right? So we can build a Nielsen theory by realizing a root is just a coincidence point, f comma some constant function, all right? And in the root theory, since C is a constant function, it actually simplifies a lot of things. So you can do a lot of calculations in the root theory that are not possible to do in the general coincidence theory. And so this is an interesting kind of Nielsen theory that's much simpler, I would say, than general coincidence theory. All right? Number 7, pre-image theory. This is, I'm going to call it like a mother theory and this is actually the paper that I mentioned before that I failed to read the little footnote in, because it doesn't seem to be about this. It seems to be about something different. This is a generalization of the roots problem. It says if I have any map, just one map, and just a subset in the codomain, and then I ask about what is the size of F inverse of A under homotopies of F? This is the pre-image. How many, what's the cardinality of the pre-image of that set? All right? This is more general than root would be if this is just a single point. but this is more general about a larger set, right? They define a pre-image Nielsen number, n of f comma a. It counts how many x there are in the domain which have f of x in the set A. I don't know if this sounds like a mother theory to you, but actually this single theory generalizes all of fixed point and coincidence and root theories. For example, the coincidence set can be expressed in this way as f cross g. This is the Cartesian product of the functions f and g, the inverse of that, the inverse image under that of the diagonal in y cross y. This is a little complicated, you have to work this out, but you will realize that all of these things that we talk about f of x equal x or f of x equal g of x, they can all be realized as pre-images, usually of diagonals inside of the image space. So this is kind of a mother theory. Super general, and for that reason, it's actually very hard to calculate anything in this theory because it's so general, but it includes all of these other ones. Super general about the types of points that it measures. But one weakness of that theory is that it allows all possible homotopies of the map. And this remains an extremely hard thing to work with in Nielsen theory. What if we only want to allow certain types of homotopies? Not every possible homotopy, but only certain ones. And this is the major issue in the periodic point theory. Remember I said we're basically looking at the nth iterate, but we don't want to allow all homotopies of the nth iterate, only the ones which come from homotopies of the original map F. So the general question in Nielsen theory of considering some but not all of the homotopies, this is actually very difficult and not well understood in general. So I would describe this as like an overarching open problem for Nielsen theory. It's something like if you have a function f and some set of like good homotopies that you want to talk about, you don't want to allow all homotopies but only certain ones, can you define a Nielsen number with this h which allows only those good homotopies and not the other ones? All right, this is actually, I think probably this is impossible in general, but anyway, this is a not well understood at all at this point. I'm not sure how reasonable it is to expect this kind of thing. All right, but anyway, this would allow you to generalize periodic point theory and also many other types of Nielsen theory, which I'm about to talk about, the last two, I think. Number 8, there has been a Nielsen-Borsuk-Ulam number. All right, so I hope you're familiar with the classical Borsuk-Ulam theorem, which is about a sphere and the involution on the sphere. So this is not just for spheres, but given a map, these are typically manifolds, and a free involution on the domain, I want to count points in a homotopy invariant way which have this property. This is the Borsuk-Ulam property in a homotopy invariant way. And again, since I'd see something equals something, I think maybe I could do a Nielsen theory with this, all right? We want to minimize the number of these, they call the Borsuk-Ulam points with respect to this involution. We want to minimize those points by changing f by homotopy, all right? And again, this looks like a coincidence problem, coincidence of f, comma, f composed with the involution, right? That's what this is. But in the setting of the Borsuk-Ulam, you only want to change f by homotopy. If you just look at Nielsen coincidence theory, you would change f by some homotopy, and also you would change f composed tau by some other homotopy, but this is not what we want. We want to only change f on both sides by the same homotopy, all right? This is one of those kinds of restricted homotopy situations, and so it's very difficult to treat this in the same way. And these are some Brazilians. The Brazilians are really into this Borsuk-Ulam stuff. So Kotram and Vendruscolo defined this Nielsen-Borsuk-Ulam number, which is a lower bound for the number of points like this if you change f by a homotopy. Again, from my understanding, this is very hard to compute, but they have the definitions at least. All right, and I got one more, number 9. We made it before the end. Relative Nielsen theory. This is developed by Schirmer again in the 80s. Here's an example to kind of motivate the relative theory. If I consider this unit disk in the complex plane, z goes to z to the 6th. This has, at least along the edge, it has 5 fixed points. It also has fixed points on the inside also, but I want to concentrate just on the 5 fixed points on the edge, all right? Now, because the disk, the whole thing is contractible, obviously you can change, f is homotopic to a constant on the whole disk, and so you can make it so that this has only one fixed point. But when I look at this, I think I would like to keep the same on the boundary, but see what can happen if I leave the map the same on the boundary. This is called a relative So the Nielsen number, the classical Nielsen number is just 1. So you can combine these all into one fixed point if you push them into the middle. But what if we want to require that the boundary is preserved by the map? And I mean the boundary is preserved during the homotopy. So as you're changing f by the homotopy, you always keep the boundary preserved. On the boundary circle, if I look only on the boundary, the Nielsen number is 5, which is much more than 1, right? So if we preserve the boundary during the homotopy, then actually these 5 points cannot be combined because they have to stay on the boundary. And we know that on the circle, this map has a Nielsen number of 5. All right. So all of this, what I'm saying, this is about pairs of spaces, x comma a, and what we call relative maps. So these are maps where the f goes to x goes to x, of course, and also the subset a is always mapped into the subset A, all right? And Schirmer defines this Nielsen number. She called it the relative Nielsen number. Actually, Bob Brown has tried to popularize. He wants everybody to call this the Schirmer number, although I've heard him say it and not a lot of other people have said it. But it's unfortunate, this is called Nielsen theory, and every time somebody creates a new idea, they always call it like the Nielsen something, something, something. So there's never opportunity to name something after anybody else except for Nielsen. Everything's called Nielsen, even though Nielsen never heard of most of these things. But anyway, this Nielsen number counts the fixed points of the relative maps, which are relatively homotopic. So if you only consider maps which take the subspace into itself, and during the homotopy, all of the homotopic maps take the subspace into itself, all right? If you consider the boundary here, this would count fixed points of the boundary-preserving maps through boundary-preserving homotopies, all right? And that is a useful thing to discuss in many cases. It's also very similar to some current work here. These people, these famous mathematicians that I'm sure you recognize the names, a lot of their work has to do with fixed points where you have this subspace which maps into itself and how to handle various things like that. So check those out. Ask them about it. All right, I think that's all I have. Thank you for your attention. Thanks a lot.